Okay, let's go. We've been talking about the Riemann mapping theorem, but let's move away from the Riemann mapping theorem to a new topic. I don't know why that cursor's there. New topic. So let me give you a slightly historical, a little bit of history, a little bit of historical discussion. So, you know, Newton and Leibniz, these are the sort of co-creators of calculus as we know it. Leibniz learned a fun problem. Leibniz, is it I then E? I think it's like that. Does that look right? Yeah, Leibniz solved a problem that was given to him apparently by Huygens we say in the US, but I think it's Huygens in what is it, Dutch or something. Leibniz solved the following problem: compute the series of the reciprocals of triangular numbers. So what do I mean by triangular numbers? You guys know triangular numbers, right? This is like a elementary topic. So this is 1, this triangle is 3. You add another triangle, you get 6. You add 4 to that, you get 10. You add 5, you get 21, right? So these are the triangular numbers, the sum from 1 to n of j, which everybody knows, n times n plus 1 over 2, okay? These are the triangular numbers. And what Leibniz is being asked for is the series 1 over 1 plus 1 over 3 plus 1 over 6 plus 1 over 10 plus 1 over 21 and so on. So this is the sum of 2 over n times n plus 1. Okay? And Leibniz is very clever. Well, first of all, he pulls out the 2, and then we have a 1 over n times n plus 1. And Leibniz realizes that this you can express as 1 over n minus 1 over n plus 1, because when you cross multiply, you get n plus 1 minus n. That just gets you a 1 on top and an n times n plus 1 on bottom. And so actually this series completely telescopes. This 1 we can write as, so if I pull out a factor of 2, then I'm left with a 1/2 plus a 1/6 plus a 1/12 plus a 1/20, and so on. And a half is 1 minus a half, and a 6 is a half minus a third, and a 12th is a third minus a quarter, and a 20th is a quarter minus a fifth, and so on. And it just telescopes all out, and you get 2. Cool? Nice and simple. Everything was peachy keen in the early days of calculus. This is like 1680s or something, 1690 maybe, 1690s. And the next question was, okay, next most obvious question is sum of reciprocals, not of triangles, but of squares. In other words, 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over whatever 5 squared is, and so on. And this problem, so term by term, this is smaller. So this is less than 2. In fact, they could work it out. I forget what it is, 1.64449 something. I don't know what. They could work out the decimal values. They knew it converged. They just didn't know what it converged to. You guys probably all know what it converges to. Raise your hand if you know what it converges to. Okay, so most of you, okay, so some of you do, some of you don't. That's okay if you don't. This became known as the Basel problem. Basel problem. And it remained basically unsolved. So Leibniz taught this to Bernoulli's, first Jakob Bernoulli, the older brother of Johann Bernoulli. So Jakob didn't know how to do it. Johann didn't know how to do it. Johann had a young student that he was tutoring. Anybody know who Johann would give Saturday morning math lessons to? A young fella named Leonard. Leo. Leonard Euler. So Johann tutored Leonard Euler. This is in the 1720s. Euler, 1727, Euler fails at his job search. Despite being already a very brilliant mathematician, he's winning first place in the Parisian Academy, the French Academy of Sciences, for all kinds of wonderful papers that he's writing. He does not get his coveted job at the University of Basel, which is where all of these great Bernoullis are. In fact, even the Bernoullis can't get jobs at Basel anymore. They have all the jobs in Basel. And Daniel Bernoulli, so Johann's son, Daniel is in St. Petersburg, where they're trying to set up an academy, the St. Petersburg Academy of Science. Peter the Great is trying to rival the Berlin Academy and the Parisian Academy, and Euler goes there as well. And it's not until 17. So he's like, you know, he's a great mathematician, but he's having trouble getting a job. What can you do? You think it's a modern problem. It's been around forever. 1734, he finally solves the Basel problem. So I want to explain to you his solution, and breaks open the field of analytic number theory. But the solution, okay, so let's see what he does. So here's Euler's brilliant idea. So this problem had remained open for what, 40 some years, almost 45 years, something like that. And the greatest minds couldn't do it. They couldn't do it. It's kind of funny, like rigor is non-existent in these days. And yet they can do all this incredible calculation with just bare hands. But you still needed a little bit more ingenuity. So here's what Euler stumbles upon. So here's Euler's idea. Okay, first of all, we know the series expansion for sine, as did Euler, z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7 over 7 factorial, and so on. Presumably, you all know that this is exactly what he used to show that e to the I theta is cosine plus I sine. So he's well aware of these kinds of things. And of course, e to the I pi is -1. This is all classic Euler type stuff that you learn in grade school. So he knows this series expansion, which proves this, and this proves this. And he has a crazy idea. So first, let's divide out by z. So sine z over z has a leading term, which is 1. Sine z, right, has a 0 at 0. And so if I divide by z, I get a nice holomorphic function. Of course, he's not thinking about holomorphic functions. He's not thinking about complex analytic functions. Surprisingly, you would think once you have this formula, how can you not put the real part on the x-axis and the imaginary part on the y-axis? You parametrize the circle. You know that sine squared plus cos squared is 1. How could you not see it? Historians apparently tell me, I always sort of attributed this to Euler, but historians say that no, Euler didn't know it. Okay, so this is z squared over 3 factorial plus z to the 4th over 5 factorial. I haven't done anything. Z to the z to the 6 over 7 factorial, and so on. Okay, what does this function look like? So again, at 0, it's now of size 1, and then it decays like 1 over z. So if this is 1 over z, or 1 over absolute value of z, it still has the same zeros as sine, except for the 1 0 that we removed at z. So at pi, there's a 0 at pi, there's a 0 at 2 pi, and at negative pi, and at negative 2 pi. So the function does something like this. Boom, 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 and it gets smaller. Okay, so this is sine z over z. So far, so good? Now, here's where the leap of imagination, the leap of faith comes. Here's his observation. If I have a polynomial, p, let's say in, again, he wasn't thinking about it in these terms. And I know that the value at 0 of this polynomial is 1. So p at 0 is 1. And p has roots alpha 1 through alpha d. So it's degree d. Okay, if I have a degree d polynomial, I know what the roots are. The roots are, of course, none of them are 0. And its value at 0 is 1. Then I know the polynomial exactly. Let's call it p of whatever. Z, x, doesn't matter. What's p of x? Can you think of a polynomial that has roots at the alpha I and its value at 0 is 1? Well, let's just think of a polynomial that has, let's say, degree 1. So I just want a polynomial that vanishes at alpha 1 and takes the value 1 at 0. Bertrand, you got one for us?
X minus 1.
X. Yeah, so if we did x, so we want the root at alpha 1. X minus alpha 1 is a good guess. The problem is at 0, it takes the value alpha 1. So we want to divide by negative alpha 1. So in fact, if we take 1 minus x over alpha 1, does everybody see that this at alpha 1 vanishes and at 0 is equal to 1? And the nice thing about being 1 at 0 is that that's something that's sustained under multiplication. 1, and if a single value is 0, then the product is 0. And if all the values are 1, then the product is 1. And so this is the neat observation that Euler has. So if you have a degree d polynomial, why is it uniquely determined? If it's degree d, then linear algebra tells you need d plus 1 pieces of information. We have the d roots, that's d pieces of information, and its value at 1. That means that polynomial is uniquely determined, and this is exactly the determination, right? This degree d means d plus 1 coefficients, d plus 1 pieces of information, and we're given d plus 1 pieces of information. Okay. That's all fine and good. Here's the leap of faith. Then, so this is what we're going to take a little bit of time to justify, which Euler didn't. So people didn't believe his proof, but they went along with it. Then this polynomial, sine z over z, of course it's a degree infinity polynomial, but I know where his roots are. His value at 0 is 1. So I should be able to express it as 1 minus z over, I have a root at pi. I have a root at negative pi. I have a root at 2 pi and a root at negative 2 pi. And of course, these are differences of squares, so we can group these. So if I group the next one, I'll get 1 minus z squared over 3 pi and negative 3 pi, so I get 9 pi squared. You guys see that? And then 1 minus z squared over 16 pi squared. And he makes, you can graph these things, and you can see that this thing seems to, in the limit, be getting closer and closer to this curve. So we're matching the curve. So this is what needs justifying. This is unrigorous. And this is what we'll spend the next bit of our time doing. This is what Weierstrass and Hadamard sort of figured out how to do. A complex analytic function, an entire function, is basically determined by its zeros. So Euler got a little lucky here because he knew what the real zeros were. But sine, for all he knew, since he wasn't thinking about complex analytic functions, could have had complex zeros. Sine z over z could have had complex zeros. It turns out it doesn't. But if it had complex zeros, this would be really wrong. So then what? So now you have all the information that you need to solve the Basel problem. What does he do? Maybe it'll help if let's combine the two pieces of information. So sine z over z on one hand is equal to this series, 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial minus and so on. On the other hand, it's the product, 1 minus z squared over pi squared. Now I'm grouping these in pairs. 1 minus z squared over 4 pi squared, 1 minus z squared over 9 pi squared, 1 minus z squared over 16 pi squared. What do you notice? What do you wonder? This is some sloganeering.
Well, I guess
Thomas?
if you take like if you power expand the right side and look at the squared term, you know.
Yes, exactly. Expand this. Exactly. Expand. Now, if you expand, you get a giant mess, but just look at the z squared term. Let's look at the z squared term. So how can I get a z squared? Well, I can do, there's no z's, so I can do a z squared and then all ones, 1, 1, 1. So that'll give me a minus 1 over pi squared. I can also do this z squared and all ones. So that gives me a minus 1 over 4 pi squared. Or this z squared and all ones, minus 1 over 9 pi squared, and minus 1 over 16 pi squared, and so on. But if I look on the other side, what's the z squared term? It's right here. So if I multiply through by negative pi squared, I get pi squared over 6 is 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and so on. Okay, so that's this number. That's this magical number that Euler identified. Cool? This shot him instantly into worldwide fame. A lot of people knew about the Basel problem. Nobody could solve it. You know, he's better than Leibniz and Johann Bernoulli and Jakob Bernoulli. And, you know, this guy publishes, what, 92 volumes of his collected works and continues publishing posthumously for almost 50 years. After he dies, people are still finding notes in his desk drawer that he hadn't gotten around to publishing. So anyway, he's one of the most prolific. Hey, I don't have to sell Euler to you guys. You know who Euler is. Sriram?
So you will get the formulas for the reciprocals of products of squares if you compare the z power 4 terms and so on.
Ah, yes. If you look at the, then he does that. He does that. He looks at the z to the 4 term, looks at z to the 4 term, and some of those terms will come from squares, and some of those terms will come from you'll sort of you have to multiply this out. Exactly, it's products of squares, and the products of squares can come in a variety of flavor. There's a little bit of algebra you have to do, but he looks at the z to the 4 term and he works out. He finds the 1 over 1 plus 1 over 2 to the 4 is 16, and 3 to the 4 is 81, and 256, and so on. So this is the sum 1 over n to the 4. He finds in terms of pi's, I don't remember what it is. Does anybody know? Pi to the 4 over some Bernoulli number. So powers of pi's times a rational number, which is a Bernoulli number. Bernoulli number. And he does this for all even powers. So the sums of the reciprocals of the even powers we know exactly from Euler, from this kind of calculation of Euler's. By the way, does anybody know what the sum of the reciprocals of the cubes is? So 1 over 1 plus 1 over 2 cubed is 8, 3 cubed is 27, 4 cubed is, did I get this wrong? No, 64, that's right. 5 cubed, 125, and so on. Does anybody know? Raise your hand if you know what this sums to.
Is it a sum a Paris constant or something?
Well, so Apari proved in the 1970s that that this is not rational. So, but yes, no one knows. No one knows. Still today. So this is unknown. Only known that this is not a rational number, which was proved by Apari in, I want to say 70s, 1970s, not 1670s or 1770s, 1970s. Okay, so we don't even know that this number is transcendental. We know nothing about it. It's presumably algebraically independent from any other number that we know of. Okay, so Euler got very lucky. If they were interested in the sums of reciprocals of the cubes for some reason, he would have a very hard time finding a job. By the way, soon after this, he moved to the Berlin Academy, which where he stayed for a long time. And then in the 60s, he went back to St. Petersburg, where he died. Anyway, there's another thing that Euler does as a result of this that I want to tell you about. He sort of gets this idea that sums on one hand, so this, by the way, I mean, he introduces this notation, the zeta function, zeta, which today we use the letter S. The letter S is because of Riemann, is to say, is by definition, the sum as n goes from 1 to infinity of 1 over n to the s. So this would be zeta of 4. This is zeta of 2. And this is zeta of 3. So we don't know what zeta of 3 is. So this is, there's a fun line, which is this thing is the Riemann zeta function. It's called the Riemann zeta function, which you will see very soon why it's called, why it really does deserve to be called the Riemann zeta function. But it's a Dirichlet series, defined by Euler. Anyway. Why does Euler, what does Euler do with this? He makes the following crazy observation. So if I look at 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus 1 over 5 to the s and so on. So this is zeta of s. He realizes that he can do the following thing. If you take just the powers of 2, that's an s, and you multiply that by just the powers of 3. Now you're testing my knowledge of powers. And then just the powers of 5. 5 to the 2s, 5 to the 3s. And just the powers of 7. And so on. So you take this infinite product over all primes. I claim you get the same thing as just adding up all the numbers. Why is that? Does anybody see why that might be true? So for example, the number 12. Yeah, go ahead.
For prime factorization?
It's the unique factorization. Exactly. It's the unique factorization. It's equivalent, in fact, to the unique factorization of any natural number as product of primes, of prime powers. So for example, 12 is, of course, 2 to the 2s times 3 to the s, and that will happen at this term in all ones. Does everybody see that? So every number uniquely is a product of some power of some primes, and those primes and those powers happen exactly once in this list, and then you just choose ones for the rest of the products. Does that make sense? You can do this rigorously. If you do it rigorously, what you're really saying is when you take the product of all the primes up to some amount, up to 100, well, then the series, then the two series agree for the first at least 100 terms. since they have by this unique factorization. And so your error term starts from the 101st term and up. But the series, so this series, of course, converges only if S is, when does a series like this converge? You compare it to the integral 1 over x to the s. 1 over x converges as long as, 1 over x to the s converges as long as
S is greater than 1.
s is greater than 1, yeah. So if you compare this to the integral of 1 over x to the s dx from 1, not from 0, which converges only if s is greater than 1. And in fact, we can make it, since this is complex analysis, all that matters in absolute value is the real part, right? N to the 1 over n to the sigma plus it. Now I've switched to Riemann notation for things. So in Riemann's world, instead of z being x plus iy, it's just, I can't help it, and neither can anyone else. Historically, Riemann's paper on this was so influential, he used the notation s is sigma plus it. It's like some knee-jerk thing, the letters take on a new meaning. Anyway, n to the it, of course, what do I mean by this? I mean, n is just a natural number greater than 1, so I can use regular old logs. By this, I mean the exponential e to the sigma plus it times log n. And this is a nice real number, so the absolute value of this is just e to the sigma log n, which is 1 over n to the sigma. Okay, so this real part of s being sigma greater than 1 is where this thing converges. Anyway, so if the series converges, and if you take the first 100 primes, then they agree on the first 100 terms, and you take 100 out to infinity, the fact that this series converges tells you that the limit, in the limit, these things agree. Okay, we're not at the point yet where we're doing rigorous stuff. We will in a minute start doing rigorous stuff. I just want to kind of tell you the story of why we're doing the things that we're doing. So far, so good? Okay. So in 1737, he proves an incredible theorem. So this is called the Euler product formula. This is the Euler product formula, which people will more often write that the sum 1 over n to the s, n greater than 1, is the product over all primes. Now, each of these is a geometric series. Convergent geometric series. So it's 1 over 1 minus, this is lambda. So this is lambda, lambda squared, lambda cubed, and so on. So this is 1 over 2 to the s. And the same thing with 1 over 1 minus 1 over 3 to the s, and 1 over 1 minus 1 over 5 to the s, and so on. So for a general prime, it's 1 over 1 minus 1 over the prime to the s. Does that make sense? By the way, this gives a really funny formula. So we know that zeta of 2 is, what did we say, pi squared over 6, which was this sum. But it's also the product over all primes. Let's see if we can work this out. This is 1 over 1 minus 1 over 2 squared times 1 over, now let's play with this a little bit. Let's put a 2 on, so this thing is the same as 1 over 2 squared minus 1 over 2 squared. So I think I can do that. So here I get 3 squared over 3 squared minus 1, and 5 squared over 5 squared minus 1, and 7 squared over 7 squared minus 1, and so on. And so you get this really crazy formula for pi. Let's see. I want to multiply by root 6 and take by 6 and take square roots. So I think if we take root 6, and if I take square roots of this, I get 2 over root 3. 2 squared minus 1 is 3. And 3 over root 9 minus 1. And 5 over root 24. And 7 over root 48. And 11 over root 121. and 13 over root 169, and so on, this massive product comes out to pi. And the numerators are primes, and the denominators are the prime squared minus 1 square rooted. And there's an extra factor of root 6 up front. Okay, that's just trivialities. He proves, what he does in 1737 is he proves a really beautiful theorem. Here's the theorem. Well, here's his theorem. Not only are there infinitely many primes, but the sum of the primes, if you take the reciprocals of the primes now, not 1 over the triangular numbers, which converges because it grows like 1 over n squared, same thing with 1 over the squares themselves, zeta of 2. But the reciprocals of the primes, does anybody not know what I'm about to write? I don't know if I'm boring all of you and you all know this, or if I'm going too fast because, okay, good. So some of you, thank you. Thank you for telling me that you don't know what I'm about to write. The sum of the reciprocals of the primes diverges. There are so many primes. Does everybody know that the harmonic series diverges? Yes, 1 over x. You compare it to the integral. Note, the Bernoullis were very fond of this, although it was proved. They gave a slick proof of this, although it was known long before. So there's so many integers that if you take their reciprocals, you add them up, it doesn't go to 0 fast enough. Whereas 1 over n squared does go to 0 fast enough. The primes, there's too many primes. There are so many. This was the beginning of our understanding of just how many primes are there. There's so many that they're reciprocal. There's so many more primes than there are squares, for example. Because 1 over the squares converges, 1 over the primes diverges. And this was the birth, this is the birth of using analysis in number theory. The primes are these discrete things. You're not supposed to be able to, say something using continuous integrals about prime numbers, right? Primes are these weird, we don't know when the next one is. It's hard to tell which numbers are prime or not. Actually, that's not that hard. Anyway, that's a whole other story. So let's prove this theorem. Let me show you Euler's proof. It's very simple. Let's take, so I know that zeta of s goes to infinity as s goes to 1, right? That's this. This is zeta of 1. So whatever this sum is, he's again only thinking about the real valued function. It's blowing up. It has this, as we'll see, it actually has a pole at s equals 1, this zeta function. But we need Riemann's extension to be able to do that. So this blows up as x goes to 1, which means this product blows up as s goes to 1. But let's look at this product. Let's look at log zeta s. The reason I want to look at log is because I have a product, and products and logs play nice. So this will be a sum over the primes, p. I'm getting ahead of myself writing the zeros of the zeta function. We'll get to that eventually. Of log of 1 minus p to the s to the minus 1. This is now the real logarithm. This is no funny business with complex numbers. He's just dealing with the real logarithm. He knows the series expansion. He knows that negative log of 1 minus x, if x is small, let's say x is less than, I don't know, a half in absolute value or something, he knows the expansion. What is it? X plus x squared over 2, I think this is right, plus x cubed over 3, no factorial, plus x to the 4th over 4, and so on. I think that's right, because if I differentiate both sides, let's differentiate both sides. On this side, I get 1 over 1 minus x with a minus 1. And on this side, I get 1 plus x squared plus x cubed. Yes, so I get the geometric series. That's correct. And so these two are off by a constant, but the constant is 1 because as I send x to as I send x to 0, I get log of 1, which is 0, which is also 0 on that side. Okay? So if you use this expansion, what you get is a sum over the primes. I have x. X is p to the minus s. So that's 1 over p to the s, plus all of these other terms. But all of these other terms are bounded by things that like the sum of p to the 2s, which I can estimate by the sum over all numbers, two powers. Okay? Maybe I start at 2, just to make sure I get a little bit of savings in these powers. Should I work out this error term more precisely, or you believe me that this error term is bounded, basically? Everything that's here is big O of 1. Thomas, you buy that or no? Should I be more precise?
Sorry, I had to deal with something else real quick, so I missed that, but it's okay.
Kayla, do you buy it?
Yes.
Okay. So so the rest of the terms, all these lower order terms, they're contributing larger powers, larger prime powers, and those larger prime powers are at worst the second power, and so I may as well throw in all the numbers, and I get something that converges. So, well, we see it right here. Log of infinity. This also goes to infinity as s goes to 1. And there's our sum of reciprocals of the primes diverging. So this goes to infinity. Because the rest of it doesn't. The rest of it is bounded. If this were bounded, if the sum of reciprocals of the primes converged, then this would be bounded, and this would be bounded, and the log would be bounded, which means zeta itself would be bounded as s goes to 1, which is not true. Does that make sense? Just to give you a little bit of foreshadowing. So in the year, in particular, this implies that there are infinitely many primes, which of course was proved by Euclid 2,000 years before Euler. But 100 years later, 1837, Dirichlet, using Dirichlet characters, manages to prove that if you restrict not to all primes, but only those primes that lie in some progression, let's say A and Q are co-prime. So this is only the primes that leave a remainder of A when divided by Q. That sum still diverges. So this was proving the infinitude of primes in progressions. So are there infinitely many primes that end in 777? Well, those are the primes that are congruent to 777 mod 1,000. And 1,000 only has 2s and 5s in its prime factorization, and 777 is not a multiple of 2 or 5. So they're co-prime. So yes, there are. So for example, this implies infinitely many primes end in 777. Okay, because 777 and 10 cubed are co-prime. Okay, so that was Dirichlet, and then we're going to get to 1859, where Riemann's memoir on Zeta, which introduces the Riemann hypothesis, and 1896 is when enough towards the Riemann hypothesis is proved. This is Hadamard. We're going to talk about all of this stuff. De la Vallée, Poussin. Is there an I or an E or an O? Anyway, I'll write them both and then I'll be safe. Hadamard and de la Vallée Poussin finally proved the Gauss's conjecture. I'll explain what all of this is. Gauss's conjecture, which is now called the prime number theorem. So this is where we're headed, but we have to do it rigorously. This is actual math and not historical math. So let's take a 5-minute break. But what I need to do is make the first step of this rigorous. So we're going to make this, we're going to start making things like this, these kind of infinite products and so on. We're going to put them on a rigorous framework, but I just wanted to foreshadow where all of this is going, which is the use of analysis. In fact, complex analysis, it turns out, is absolutely, well, we can argue about whether it's absolutely essential. In fact, number theorists argue amongst each other whether complex analysis is essential for our understanding of prime numbers or not. But that's a whole other story. Does that make sense so far? Let's take a 7-minute break. Let's get back to what I'm supposed to be doing with you people, which is not this. So, okay, let's make these things rigorous. So the first thing I want to understand, make this rigorous. Make this stuff rigorous. So here's a question. What does it even mean? What does it mean for a product of things? And it's convenient to normalize things by saying 1 plus an to converge. Well, what should it mean? Given some sequence an, sequence of complex numbers, we say that the product converges if and only if it's a definition, what? What's a reasonable definition? You know what it means for a sum to converge. The partial sums converge, as the partial sums form a Cauchy sequence. So
Wouldn't
Thomas?
you do something similar?
Yes, Kayla, exactly.
And the partial products should
Exactly.
converge?
Exactly. So let's make the partial products. So these are finite products. These are all complex numbers. And we know what it means for a sequence of complex numbers to converge if this sequence, partial products, converge. Partial products converge. Right? So here's a little, I don't know, lemma. If the sum of the ANs converges, then the product of 1 plus ANs converges. Okay, why is that the case? Well, let's look. So proof. That's why it's convenient to put this 1 plus. See, products are supposed to, if a product's going to converge, then the terms need to go to 1. That's like a net, that's, yeah, that's basically a necessary condition. Because if it doesn't go to 1, then these numbers keep getting multiplied by something that's not 1. So how are you going to get a sequence to converge if it's being multiplied by something of absolute value that isn't going to 1? So how can we prove this? Let's look at the partial sums. And in fact, let's look, of course, at the logs of the partial sums. Look at log of the partial sums. So this is a sum, as n goes from 1 to n, of log of 1 plus an. Now this is the complex log. Am I allowed to look at the complex log? Now we have to be a little careful. When do we know a formula like, remember that we were looking at this formula, negative log of 1 minus z is z plus z squared over 2 plus z cubed over 3 and so on. Did we cover this? When do you have this kind of series expansion? And where does it converge uniformly?
You have it in a ball around is equals 0, right?
Yes, yes. So this is, so if z is 0, I'm sort of taking log near 1. If z is 0, let's say less than a half in absolute value, just to be safe. So here's the place that I want to stay away from. This is uniform convergence for z, let's say, in this compact ball of size a half. Well, if the ANs converge, the sum of the ANs converges implies the ANs go to 0. So we may as well assume after finitely many of these terms, all of the ANs are less than a half. So assume that the ANs are all less than a half. Or just start your analysis after you've passed those finitely many ANs that aren't less than a half. Okay? So after a finite sum, you'll see, or a finite product, you'll see only ANs that are less than a half. For those ANs, we have this series expansion. But what can we derive from this? That means that the absolute value of log of 1 minus z, or log of 1 plus z, is bounded. The z's are less than a half. So I can pull out a z, and then I get, a half plus a quarter plus an eighth, if you like. I mean, I'm getting powers of z. So let's say that sums to something like 2. Do you see that? This is in this region if z is less than a half in absolute value. Then log of 1 minus z is bounded by twice absolute value of z. So these ANs, this series, but the sum of AN absolute value of log 1 plus AN is bounded by 2 times the sum of the ANs themselves. And by assumption, that converges. And so that implies that the sum of the log 1 plus ANs converges, has a limit, and exponential function is continuous. And so this also has a limit. So exp of log of AN has a limit. That is, the ANs have a limit. The partial products have a limit. Does that make sense? So it's exactly this translation. If you want to take products, sure, go ahead and take products. But if you want to study those products, take their logs, then you're back to sums where you're happy. Except logs shift the location of 0 over to 1. Okay, so if a series converges, then the product converges. Moreover, there's a part 2. Moreover, come on. Can this product be 0? You have a sequence of complex numbers. They could converge to 0, couldn't they? Moreover, if the series converges and the product converges to 0, well, that can't happen, I claim, unless that implies some AN is equal to -1. That is, i.e., some 1 plus AN is equal to 0. One of these terms has to be equal to 0. If one of the terms is equal to 0, then of course the entire product is 0. If one of the terms is not equal to 0 and the sum of the reciprocals, the sum of the series AN converges, then eventually the ANs are less than a half, So none of them after a finite amount of time are equal to -1. And that series converges. And when you take the exponential of a convergent thing, the exponential is never 0. The exponential function is not 0. So proof, exponential of log of an is never 0. So the only way a convergent product ever gets to 0 is if one of the terms itself was 0. Does that make sense? Okay. Good. Let us talk about convergence of holomorphic functions, products of holomorphic functions. So lemma, what do I want to call this? Proposition. Let Fn be a family of functions, be holomorphic functions on some region omega, and assume that there exists constants Cn, so that if I take Fn minus 1, well, what I want to think about is what happens to the product of the Fn's. And that's why the thing that I want to think about is Fn minus 1. So that the Fn minus 1s are bounded by the Cn's, and the Cn's, which of course are positive real numbers, converge. Then this function, this product, converges uniformly on compacta, and hence to a holomorphic function, to a holomorphic f on omega. Does that make sense? If we have this bound for all z in omega. And the proof is one line. The proof is these things are what we were calling ANs before. So for fix z in omega, let AN of z be Fn of z minus 1. Then AN of z is less than Cn, and this is uniformly. This is uniform over your favorite compact subset of omega. In fact, it's uniform over all of omega, but never mind. Let's keep it, let's state a compact sets. Hence, this family of functions, by what we just saw, this family of functions converges, and each, so let's call this Gn of z, converges and does so uniformly on K to, well, converges to F, and uniform convergence on compacta of a holomorphic, a sequence of holomorphic functions is holomorphic. It's only holomorphic on K, but K was an arbitrary compact subset of omega, so it's holomorphic on all of omega. Does that make sense? Thomas, something
Where do
you
we
don't
get
like?
the uniformly from?
The uniform is that this didn't depend on what z was. I mean, I assumed uniformity, basically.
Okay.
I'm saying assume that there's a constant independent of z, so that every z in omega has f of n at z minus 1 be bounded by this constant. And the series of the constants converges. I'm assuming uniformity and proving uniformity. Great. That's a great magic trick.
Oh, so the Cn is before the for all z. Okay.
That's right. There exists
Gotcha.
Cn so that for all z. Yes, uniformly in z. This is independent of z. Independent of z. Yeah, I'm assuming uniformity, so of course it's not so hard to prove uniformity once you assume it. Moreover, I guess this is continuation of the proposition. So claim Moreover, if no fn of z equals 0, then this limiting function, the logarithmic derivative of this limiting function, remember f prime over f is this logarithmic derivative. I guess I want to think of this as a function, is obtained by the series of logarithmic derivatives. Let's see why that's true. So if we look at this this series Gn, for each Gn, for each n, it's certainly true. Gn prime over Gn is equal to Fn prime over Fn. This is just a finite sum, right? If I differentiate, what is the chain rule? I take out one of these Fn's and then the rest of them stay. But if I divide by G, I'm dividing by the product. So it's the same as removing the nth one and replacing it by its derivative. Does that make sense? Now, does this thing converge? So this is true for each n. Does this thing converge? Remember, if you have if you had a family of functions converging to a holomorphic function uniformly on compacta, so Gn converges uniformly on compacta to f, implies G prime n also converges uniformly on compacta to f prime. That was an exercise or something. We did this long ago. Hopefully you remember this fact. And if none of the fn's are 0, so this product is never 0, that means the limiting thing is not 0. This limiting thing does not equal 0. And so by the uniform convergence, at least on compacta, the GNs stay away from 0. That means Gn of z is at least some epsilon uniformly on your favorite compact set. And so that means that 1 over G is uniformly bounded. So this converges uniformly, and 1 over Gn's are uniformly bounded on K, because the Gn's are staying away from 0 if the limiting function isn't 0, since we've assumed none of the fn's are 0. And so you have two functions, G prime and 1 over G of n, both converging uniformly. Therefore, their product, Gn times 1 over Gn, converges uniformly on this compact set. And it converges to, and each of the partial sums is this, and it converges to the product, f prime, and this converges to 1 over f. Okay. Does that all make sense? This is the kind of thing you have to just check that you are allowed to do the things that you would like to do. So far, so good. All right. What can I do in just a few minutes? I want to justify the sign claim, but I don't have enough time to do it justice. So let me not rush it. So let me state a theorem. So let's justify Euler. We continue tomorrow, thanks to the Thanksgiving schedule. We're going to justify Euler by proving the following claim. My claim is that pi times cotan of pi z is equal to a sum over all the integers of 1 over z plus n. This will be my claim. Now I have to make sense of this. This is for z not integers. If z is an integer, I have a pole here. I blow up. Cotan, of course, is this is cosine over sine. Cotan is cosine over sine, just to remind you. So this has poles. It has poles, and if I put the pi there, so we've move the poles to the integers. And this function also has poles at the integers, and we're going to prove this claim next time, but I don't want to rush it. Let's see why this would imply. So my claim implies that sine of pi z is equal to what Euler said. I'm replacing z by pi z, so it's z times the product as n goes from 1 to infinity of 1 minus z squared over n squared. So this is just a replacement of z by pi. I moved the pi over here. Okay, this is the equivalent formulation of what Euler claimed. Does this make sense?
I'm trying to remember, is this like that homework exercise with tau, or was with 1 over tau plus n, or is that more restrictive, or like with some other condition on it?
You mean this claim? Is
right.
this related to the homework exercise?
Right.
There was a homework exercise. I'm trying to remember what it was. It was something we were using Fourier analysis and the Poisson summation formula to prove something. Is that the homework problem you're thinking of?
Yeah, I think so.
Yeah.
Residue calculus, I think.
Say it again, Surya.
I think Kailash was saying residue calculus.
Right. We could do it with residue calculus too. I was going to give you a slightly slicker proof, but anyway, let's see why these two things would then be the same. Okay. So why are these two things true? Well, does this product converge uniformly for, let's say, a fixed z in some compact set? Remember what we have to do. If these are our fn's, if this is fn of z, so does this converge uniformly? Does this product converge uniformly? Of course, the z I could move to the other side if I wanted to. Does that converge uniformly? By the way, we have to discuss what I mean by this. This does not converge uniformly. This doesn't. This doesn't converge absolutely. Doesn't converge. So I have to explain what I mean by this. But let's pause for a second about that discussion. I owe you this discussion. How about these? So I have to take fn of z minus 1. So what is fn of z minus 1 in absolute value? Of course, it's just, it's by design, it's norm z squared over n squared. And so if z is in a compact set, if z is in a compact set, then this is bounded by a constant over n squared. And this converges. This series converges. Series converges. Right? 1 over n squared. So this does converge on compacta. Of course, not for all z, but it converges on compacta. And so, so we do have an infinite product here. And what we know about this infinite product by this right here is that the infinite product, so this, let's give this a name. Let's call this P of Z or something, P of Z. So P of Z converges. So P prime over P, I can do this term by term. So the first term, I get the derivative of, so one of the functions is z. So the derivative of that is 1, and the original function was z. And then I get a sum over the integers. Let's see, what's the derivative of this? Negative 2z over n squared is the derivative of each one, divided by, which I'll write as times 1 over, f. Did everybody follow what I did there? This is just f prime times 1 over f. This is f prime, fn prime. This is 1 over fn. You see what I did? Okay. Right. Let's combine these together. I believe I get a negative 2z And what do I get in the denominator? I can just multiply the two denominators together. So I'm just getting n squared minus z squared. And so if I fix that minus sign, I think I'm getting a 1 over z plus a sum over the positive integers of 2z over, and I'll negate the denominator also. I'll get that. Are you guys happy with that? What about this?
sorry,
Sorry?
why do we break this up as addition? The z going to 1 over z?
Because when we take the logarithmic derivative, it's the sum of the logarithmic derivatives.
I see. Yes. Okay.
Right? F was a product. That's the beauty of logarithmic derivatives, is that they turn products into sums, and they just turn it into term by term. Does that?
Yeah. Thank you.
Great. Now I owe you a discussion of how this converges. And you'll see in a second. What do I mean by this converges? I mean if I take n and I take the sum symmetrically. But of course, if I take the sum symmetrically, that's how I want to interpret this convergence. There's a term where n is 0. And then there's a sum over, let's say, the positive values up to n. And I'll group the positive value and the negative value. Okay, so we group the positive and the negative value together. Does anybody know what this is? Has anyone worked out what this is? I have to cross multiply. I get a z minus n over there, a z plus n over there. The n's cancel. I get a 2z over z plus n times z minus n. Burchin?
Are we missing a z on the right-hand side when we took the derivative over the function?
Sorry, say that again?
Are we missing a z on the in front of the sum?
In front of this sum?
Yeah.
I could have pulled the z out. Is that what you mean?
No, I thought we were taking the derivative, so that was the z at the front.
Yes, this.
The derivative.
You mean this 1 over z?
I was talking about the derivative of the product. So
The derivative. So I'm taking f prime of n?
yeah, shouldn't we multiply with the z at the front?
I'm just differentiating this with respect to z. The 1 does nothing. There's a factor of negative 1 over n squared. And then the z squared, I differentiate and I get 2z.
But then we have times z at the front.
Oh, this z.
Yeah.
I'm treating this z. This z is one of the functions.
Okay.
This z is one of the functions. It's like f0. And it's the beauty of the logarithmic derivative. You're worried about this z being multiplied by each of these. But we're dividing by the infinite product also. Does that make sense? Yeah, that's a very good point. This z, the role that it, when you take logarithmic derivatives, all of the products become the sums over all of the terms of the logarithmic derivatives. So this term has exactly contributed to that term, and then it's no longer part of the rest. Great question. Great question. Okay, other questions? So what happens to this 1 over z plus n plus 1 over z minus n? What does that simplify to, Kayla?
2z over z squared minus n squared.
Perfect. Okay, so this function here is exactly the thing that that's on this side. What about this? If I take logarithmic derivative of this, let's call this p f q of z. What about q prime over q? Q prime over q. The derivative of sine is cosine of pi z times pi, chain rule, divided by q itself, sine pi z. So it looks like I get a pi cotan of pi. Aha. And the claim is that pi cotan of pi is equal to this sum. Okay, we're almost there. We're almost there. So we have this P. P is this large product. Q is the function sign. Let's look at P over Q. What's the derivative of P over Q? Everybody knows the what is it called? Quotient rule. Quotient rule. Bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared, which we can simplify as P over, let's see, P prime over Q minus P Q prime, P over Q times Q prime over Q. And if I pull out a P over Q, this is a version of the chain of the quotient rule that people should learn but don't. If I pull out a P over Q, the over Q is pulled out. The P, I have to pull in an extra 1 over P, and then I'm left with a Q prime over Q. This is maybe the better version of the quotient rule. And lo and behold, P prime over P and Q prime over Q, the claim was that the two things are equal. So this thing's equal to 0. So P is equal to a constant times Q. And what constant is it? Well, if I divide by Z, this thing goes to 1 and this thing goes to 1. So divide by Z and send Z to 0, you get that the constant is 1. Okay, so hopefully I owe you this. I have not proved this. But once we prove this, then we will have rigorously justified Euler's formula for the product of the sine function, and hence his solution to the Basel problem of the sum of the reciprocals of the squares. Any questions?